from Rescue Shuttle Control. Our telemetry indicates that you succeeded in starting up your Hero controller and are ready to start working with it. That's great news. That's the first step in getting your shuttlecraft functional and ready to get you home. One of the first things that you're going to need to do is learn how to turn on the lights in your shuttle and how to control the various functions on board. Doing that is going to involve developing some knowledge both of analog circuits and of the digital computer control that's provided to you by your Hero. So we're going to walk through the basic use and the basic concepts of both of these functions during today's session. And by the end of today's session, we hope you'll have the lights on. You'll notice that in addition to the Hero device that you've got in your shuttle, which connects to your ship's computer through the USB cable, you have a white rectangular plastic board. This thing called a breadboard. Its purpose is to allow you to quickly and easily assemble circuits from discrete components. And by discrete components, I mean things like what we have here: resistors, light-emitting diodes, wires. And we will discuss what those components are and how they're used very soon. But I first wanted to sort of show you the breadboard that we'll be using in addition to the Hero controller. Now, let's back up for a moment and talk a little bit about circuits, analog circuits. A circuit is a path or multiple paths through which electricity can flow around in some sort of a controlled and closed loop. It's somewhat like water flowing around through pipes or hoses. Now, in order for a circuit to function, the circuit must be completed in a complete circuit. And that's rather similar to the idea that in order to get water to flow around in a hydraulic circuit, we need to make sure that all the water containing or water channeling devices are connected end to end. And so in order for water to flow around a circuit, it's not just sufficient to have a complete circuit, but we also have to have some pressure provided in order to make it move. The higher the pressure, the more water will move through the pipes per unit time. And so the greater the flow rate will be. However, at a given pressure, more water will flow through a larger diameter pipe and less water will flow through a smaller diameter pipe. And in our analogy to electric circuits, the voltage, or another word for voltage is potential, that's provided, say, by a battery or a power supply, is similar to the water pressure in our water example. And similarly to the idea that some pipes have greater resistance to flow and some have less resistance to flow, depending upon how wide the pipe is, we have conductors of electricity that have greater resistance or less resistance. So we call a device like this one right here that's designed to have a specific resistance to the flow of electricity a resistor, logically enough. And so a high value resistor with a large resistance would be similar to a pipe with a narrow diameter that restricts the flow of water. And a low value resistor would be analogous to a wide pipe with a low resistance to flow. Now, if we want less current to flow through a circuit, for example, we would naturally insert a resistor that had a high enough value of resistance to reduce the amount of current to an acceptable level. And we can figure out how much current will flow through a resistor by taking the voltage applied, that's like the pressure in water, and dividing that by the resistance. So as an example, our hero right here is able to supply for us a voltage of 5 volts. There's a slot right here, a pin on the hero that's labeled 5V. That corresponds to 5 volts. We also have here some resistors like this one, or the one that's currently connected to the breadboard right here, that has a resistance of 220 ohms. So if I want to send current through this resistor using my potential of 5 volts, the current that would flow would be 5 divided by 220. So if you calculate what that value is, 5 divided by 220 is 0.023 amperes. So that turns out, luckily for us, to be just about the right amount of current necessary to illuminate this device, which is a light-emitting diode. It's like a light bulb, but unlike an incandescent light bulb, it doesn't function by heating up. It functions by converting electrical energy into light. So we wouldn't want to send too much current through our LED, because if we did that, we might be at risk of burning it up. So knowing the proper value of resistance to put into our circuit to limit the amount of current is pretty important. So this is already something valuable that we've learned about these circuits, and one of the basic ideas that we'll want to understand in order to design our own circuits. But now, before we go any further with that, we have a little bit more to learn. We want to not only be able to put together an analog circuit and have current flow through it of a desired amount, but we also want to be able to control our circuit by giving instructions to the hero through our computer. Now, it turns out that by writing correctly constructed code, we can tell the hero how and when to apply voltages to certain places on the hero board and use that to, say, illuminate a light-emitting diode. Now, let's go ahead. We're going to talk about how to construct that code and how to command the hero in a moment. But first of all, let's talk a little bit more about connecting our circuit together and connecting it to the hero. One way to connect circuits together is with wires, like the wires that we have right here. But if we have to solder everything together permanently, this can be very tedious and time-consuming. And it's also inconvenient if we want to change our circuit. So, for example, if we want to revise it, or we have a new idea and we want to try a new design. So the breadboard here is there to make this job much easier, because instead of having to permanently solder components together, we can just connect parts together end to end by pushing their ends into the holes on the breadboard. The pins of our components fit right into the holes of the breadboard. And the reason why that's helpful is that the breadboard provides electrical connections between holes in the same row. So for example, all of the holes here in row 6 are connected together electrically, or all the holes in row 5. Turns out that we've also got connected holes in vertical lines as well. This red, and this blue vertical line are also connected. And although we won't use those today, we'll find that it'll be convenient for us in the future to be able to use both the horizontally and the vertically connected rows of terminals. For now, though, what we're going to do is illustrate how we might use the breadboard and the 5 volts provided by the hero to illuminate a light bulb or a light emitting diode. As I mentioned before, this light emitting diode can emit light when current flows through it. And unlike an incandescent light bulb, a light emitting diode only works properly when current flows in one particular direction. That is, in through the long prong and out through the short prong. A way of remembering that is that we need to connect the longer prong to the higher voltage. That would be to the 5-volt side. And then the shorter prong would go to the low voltage side, or 0 volts. So let's see if we can use the breadboard to connect this LED to a source of voltage and get it to illuminate. Now, as I mentioned before, there is a pin on the Hero labeled 5V for 5 volts. So we're going to take a wire and connect it to that 5-volt pin, and then connect that wire in turn to a particular row here on the breadboard. In this particular case, I've chosen to connect it to row number 6. There's nothing important about that, just pick that at random. Also connected to row 6 is one side of this resistor, this 220 ohm resistor. If I were to then connect another wire from here back to 0 volts, or ground, ground is another shorthand name for 0 volts in this circuit, then I would have current flowing through the resistor in a circuit. That wouldn't be too useful because the current really wouldn't be doing anything. So rather than simply sending a wire back to ground here, I'm going to send the current through the LED and see if we can get the LED to light. So let's connect the long end of the LED to row 10, like so. And it just so happens that the short end of the LED, where the current will be flowing out, is connected to row 11. So if I take one more wire and connect that to row 11, I'm almost ready to see the light come on. All I need to do is complete the circuit by connecting this wire to ground, to 0 volts. So let's give that a try. And sure enough, the light comes on. So that's pretty exciting. We've now figured out how to turn the lights on. When I have a complete circuit from 0 volts, or rather from 5 volts to 0 volts, passing through the resistor and through the LED, I am producing light. So that's progress, but now what we'd like to do is get the Hero involved in an intelligent way. We'd like the Hero to take over the job of connecting and disconnecting the voltage to our circuit. And so that's our next step right now. So we will, for the moment, disconnect our circuit and shift our attention for the moment to the Hero and how we can control the Hero. Now, what we have, I will direct your attention next to our code window. What you see here is that the code that is illustrated in this window has a particular sort of structure to it, a sort of syntax to it. What we'll find is that the code that's understood by the Hero consists of statements, and generally speaking, a statement ends with a semicolon. That's how you can recognize it. And you can group sequences of statements together inside these curly brackets. And so you'll notice I have one routine here called setup with curly brackets, and another routine here called loop, also enclosed in curly brackets. But there's not much inside those curly brackets yet. So our job is going to be to put some statements inside that will actually command the Hero to do something interesting. In our case, what we want to command the hero to do is to provide voltage to particular locations on the hero board. All right, so let's get started with some code. The first thing that we need to do is we need to define a variable. And in order to do that, I'm going to put a preliminary statement up at the top of this code window. And the preliminary statement is defining a variable called light. This is just a number, an integer, and I've chosen to give light the value of 12. int here means that it's an integer, a counting number, and its name is light, and its value is 12. Now, I want you to notice that when the semicolon is typed here, that's the end of the statement. And that's as far as the computer, the hero, will interpret it. But there's something after the semicolon that's fairly important. And that is, anytime you see two slashes followed by some text, that's a comment. Being a comment, it's ignored by the hero. But it's not ignored by any human being, yourself included, who's trying to read this code and understand what it's doing. So you should be getting into the habit of writing useful comments whenever you write code, because it will be a very helpful way of telling someone else what you're trying to do with your code, or it may be a helpful reminder to yourself when you come back later and try to remember what you were doing. So keep in mind that comments are very important, and we'll try to use those comments as much as possible. All right, so right now, light is a synonym for the number 12. And our comment tells us that this is going to refer to pin number 12 on the hero, so that we don't have to keep remembering that it's 12. We'll just remember that its name is light, and that's a synonym for it. All right, so let's move on. The two routines, setup and loop, have different purposes or different functions. Setup runs once, and as its name indicates, its purpose is to set up the hero, to get it started on its job. And so it only executes once. Whereas loop, which we'll get to in a little while, is designed to run repeatedly over and over again, and will not stop until you turn the hero off. So let's get started by putting some statements into setup. What I'd like to do is the following. I want to use a command called pin mode. And let's go ahead and type pin mode in so that we have an idea what it looks like. Pin mode takes as its first input right here a variable, in this case light. So we know that we're telling pin mode, I want to do something with pin number 12, another name for light. And then it has a function right here. And the function that I want to apply to pin number 12 is to make it an output. And what that means to the hero is that with pin 12, you're going to be asked to change its status, to do things to it, to make its voltage be high or make its voltage be low. So this is what pin mode does, is it assigns a function to pin number light, or pin number 12. Following the pin mode and its semicolon is another statement, digital write. Digital write now does something to that pin, in this case pin 12, and what it says is set its voltage to low. Low is just another way of saying 0 volts. So when we see high, we're going to see 5 volts, and when we see low, we're going to have 0 volts. Now actually, since we'd like to turn the LED on, let's change from low to high. And that way, when this is executed, pin 12 will now be at 5 volts, and that could be very useful to us. So let's go ahead and see if it works. Let's come back over to our circuit, and instead of taking our wire here and connecting row number 6 to 5 volts, which would turn the light on, let's connect it instead to pin number 12. So pin number 12 is right here. And not surprisingly, nothing's happening. The light's not on. And the reason why the light is not on is right now, since we have not run any code, pin 12 has no assigned function to it. So let's go ahead and upload our code to the Hero and see what happens. So we upload our code, and the light comes on. So we've now succeeded in turning on the light, but without actually touching the circuit. We've allowed the Hero to do that for us. And we can change the status if we want. If we change the code from saying voltage high to voltage low or 0 volts, we should now have no current flowing. And so if I upload the code now, the LED goes off. So that's some good progress. We've now succeeded not only in turning on the LED, but controlling the LED being on or off by giving commands through the Hero. Now, that's interesting, but we haven't even touched the loop function yet. And that is going to be very interesting for us because the loop function allows us to do things repeatedly. So let's see if we can't do something a little more interesting by putting some statements into the loop function to be executed repeatedly. All right, so I'm going to use digital write again, but I'm also going to use a new function, and you'll see what that function is in just a moment here when we take the code and we paste it in. You'll notice, by the way, while I'm doing this, that we did have an appropriate comment in setup. We said that we are initializing the digital pin, in this case pin 12, to set its value to high. Now, what we're going to do in loop is we're going to change the status, and we're going to do this repeatedly as long as the Hero is turned on. So the first statement in loop does something that might seem a little pointless, and that is it says, change the value of light to 0 volts, to low. Well, it's already off, so it might seem like a sort of a pointless thing to do. But stay with me, because what we're going to do in our next statement is execute something called delay. Delay simply waits for a specified period of time. In this case, it waits for 1,000 milliseconds. And since a millisecond is 1,000th of a second, this waits for 1 second. And then it goes on to the next statement, which is digital write, turn the light to high. And so this will turn the light on after 1 second. Now, there's another delay for 500 milliseconds, or in other words, 1/2 of a second. And then this whole sequence will just repeat. So if you think about it now for a moment, when I run this, what it should do is wait for 1 second, then turn the light on, leave the light on for 1/2 a second, and then turn the light off again, and do that repeatedly, blinking the light on and off for 1 second, on for 1/2 a second. So let's check and see if when we upload our code, if it functions in the way we expect it to. So right now we can see there's no light on. Let's upload our new code, and once it starts to execute, we have off for a second, on for 1/2 a second. On, off, on, off, on, off. So that's just what we were trying to accomplish. And you can see that we can customize this in any way that we might like. So for example, we might say, well, you know what I'd really like is I'd like the light to be off for 2 seconds. And so I could do that by simply changing the value that I set to delay to 2000. So that would be 2 seconds. And then I might say, I really only want the light to flash for a brief period of time. So let's change it to 1/10 of a second, or 100 milliseconds. Okay, so that's my new code. So if I re-upload that to the Hero, it should change the rate of flashing. Let's see if that works. Okay, upload, and here we go. 2-second wait, 1/10 of a second flash. Well, I think you can see now how we are able to use the digital controls of the Hero to control our analog circuit and do something mildly interesting with the lights here, flashing them on and off in a specified pattern. And if you wanted, you could probably experiment a little bit on your own. You might be able to write yourself some code that will flash out a message in Morse code, or do something else that might be interesting in terms of turning the lights on and off in some specified way. But for now, we've been able to demonstrate and work out the basics of both an analog circuit and its digital control, and that's just exactly what we wanted to do in this session. So for now, you can go ahead and practice with this, and we'll sign off for now. And next time, we'll see if we can do something even more interesting using our breadboard and our Hero controller. So for now, remember, invent safe, and we'll see you next time.